This is a video demonstration for EE533's Lab 5, which is about the design of a mini-intrusion detection engine. So, we in this video we'll go over the key design ideas, some of our observations in the simulation, and the best practices uh, we derived because of some problems we went through during the lab. The key design ideas. So, so basically, we're designing an intrusion detection system. So the key thing is pattern matching. So in here we are matching a 7-byte malicious pattern with our data input, and we have a 8-byte data frame. So to match this 7-byte malicious pattern with our data frame, if and to cover the all corner cases, we will need two successive frames. So let's say, what if in my previous frame, or you can say the current data frame, the first byte of the malicious pattern lies on the last last byte of my data frame. So I need to move on to the next frame to match the other remaining 6 bytes. So this is the need for having a 14 byte wide data frame to successfully match my malicious pattern. And there's one more question. Why do we need like 6 byte from the previous frame to make up a 14-byte comparison? So let's say on my byte 3, I have a matching pattern. So, but the last byte of the malicious pattern is in the next frame. So that's why that's why I need the maximum is the 6 byte from the previous frame to make up a 14-byte. So this is how we are covering all the corner cases. So at this moment, it is kind of a naive pattern matching algorithm. To improve this, we there's an introduction of a concept called a mask. So it is kind of like a smart matching algorithm. So it is actually possible that an attacker can change a few bits in the pattern in order to evade pattern matching algorithms. Similarly, some genuine data but matching the pattern can appear in the incoming traffic. So in order to avoid these scenarios, a 7-bit A mask is introduced. Whenever the specific bit of the A mask is set, the corresponding byte of the pattern is not compared with the incoming traffic. So you just it's just I mean the pattern matching algorithm gets just smarter. And what if we are detecting a pattern? So we drop the entire packet from the beginning of the uh, packet to the end if we get a successful detection. Design components. So the first design component is detect 7b. What it does, it matches my 14-byte data with my reference 7-byte malicious data, and also incorporates the a mask value and produces a match or a no match signal. Here we have a comparator. So I would like to point out that this is not a simple comparator, just a normal comparator. It has, we can see we have introduced the concept of a mask matching here. So for every comparator, we have a mask value. So 7 comparators, 7-bit a mask going to each and every output of the comparator, and this would lead to selective byte comparisons to yield a final match signal. Word match, as the name suggests, we have 8 comparators. It is matching each and every byte of it, and we get a match signal. Res 9b. So Res 9b actually it's a 9-byte data, 72-bit. So the front of the data is of my control signals, followed by my rest data input, which is a 64-bit. So this is how my final schematic looks like of my drop FIFO. So what it does is It has a dual port memory with its input data fed by a Reg 9B, which is feeding 72-bit byte data in it. And obviously, if it's a FIFO, we need write pointers and read pointers. So that's why here a couple of counters and D flip-flops exist to cater to this. So let me go through the right pointing mechanism. So so we have right a right WP counter, and its input is fed by a right pointer history register. So let's assume for a case upon reset, this is at 0, and the counter and the dual port FIFO, it's chip enable, it's connected to my FIFO write register. So if my intent is to write, this will produce a signal which will enable the chip enables of my both write counter and my dual port memory of FIFO, and this would help me, advance and write as the data flows in from the Reg 9B. Now, why this write pointer history register exists? This is to store the previous write pointer value. So, in a case where uh, between the first word and the last word, I get a signal of drop packet. So, what this drop packet does is, so what this drop packet signal would do is enable, yeah, so it'll enable the load enable of my write counter, and it will force my counter to take the input from the write pointer history. So let's say my write pointer was at 45, but the drop packet signal got high. So it would and hence it would make the load enable of this counter high. So this would make it take the make it take the data from the from the write pointer history. So it would take the old value of it. So essentially it has dropped the packet. I would like to go over the read pointing mechanism. So in here we have a read counter, which is kind of an RP, and its chip enable is controlled by two comparators, which two comparators. The first one is comparing my write pointer with my read pointers addresses, and the second comparator is comparing the previous write pointer, which is coming from my write pointer history register, to my read pointer, the read address. And upon if there's a equality check, if it'll produce a chip enable and it'll control how my read pointer works. And obviously in a system we always have a valid data signal. So upon if I need to read the data, I need to know that if it's a valid data or not. So this is for this is there for that for we have reached the end of the packet, and the user can read it if my valid data is high. That means it's a meaningful data. Some key observations in the simulation. So there are like two key observations I would like to point out. The first one, the data input. As we can see, let's focus on timestamp 1100 nanoseconds. So DIN and in data, these both are from my test bench, my input data. And as you can see, right here is the data I'm getting from my infifo, which is the input to my Reg 9B. So what I want to try to convey here is there is actually a three clock delay between my test bench data to my, in comparing values we need to make sure about this delay. The second one, yeah, so let's see how our system is actually working. So upon a successful comparison, a signal called match will go high. That means we in the data stream we have detected a match, a malicious pattern. So let me go through this. So yeah, this is the instance where let's focus on like 2600, 1200, 600 nanosecond timestamp. So here the match and match signal is high, and as we can see, this XLXN13, this is my WP counters output, and my WP counter is at 40 right now, and this is XN12. This is my right pointer history register, which is at 34. So when as soon as it detected uh, there's a match between my first word and last word, it drops the packet, and the WP counter resets and loads the value from right pointer history, and it goes back to 34. Another case I would like to point out is upon a successful end of the packet. So how would we know it's an end of the packet? From the last word signal. So let's say, let's go back. Yeah, here. So you can see last word signal is high, and here my WP history is 0. So when at the end of the packet, given there's no match a match signal, there's no detection of a malicious pattern, my right pointer history goes to 17. So proceeding to 17 gets the old value of my WP counter. So this is how my system is working. Let's go to the slide deck. So some key learnings. So I would suggest uh, always like make the design from ground up. So basically we're making the comparators first, moving to the word match and reg 9b. So we shouldn't start from the top module. Always go from the bottom to the highest your desired, which is your aim top module stuff. Yeah, another important thing: device selection. So make sure to select this device vertex 2p and this device code. Yeah, because other versions of the FPGA, I mean, they're not having support of dual memory IP core, but this one seems to have, and it does work. So be careful of that. Yeah, the last one. How do we generate the memory block, which is the IP core, in our draw FIFO schematic? Just go to the new source, and then you need to go to the basic elements. Go to the basic elements, drop down the memory elements, and you need to select the dual port block memory. And here it'll ask you to configure your IP block. So uh, in the port A options, you have to select write only and no read on write. And for the port B option, we need to select read only. How do we know it's for port A, it's for the write, and how do we know for the port B, it's for read? Okay, I mean, this is a draw fiber schematic, so you can see the A port is driven by the write addresses. So this has to be, the port A is meant for my write point, write action. Similarly, for my B port, it's meant for the read. Thank you.